So on Friday, there's going to be a special ceremony of excellence for you in honor of like dedicating yourself to excellence for the rest of the semester and recognizing the good grades you've already gotten. Let's go ahead and get signed in. Perfect. And your name is Anthony, right? Yes. Perfect. And your name is Isaac? Yes. Perfect. That's all right. No worries. I was actually almost late myself. In fact, I actually was late. I was like 30 seconds late because of the traffic jam. So let's see. Let's go ahead and get started. And now we're in chapter 2. So that's exciting. So there are a couple different ways of thinking about this. So what is the idea of a set? So how many of you have done computer programming a little bit already? Like, what are some different data types that they have that you could store more than one thing inside of? A list, and what else? An array? Any other kind of thing? Dictionary? Any other kind of thing? And then some languages have different names for the same thing. So you might have like a hash in Perl or an associative array in some other language, or you might have like an object in JavaScript. There's a lot of different names for them. So in a way, all of those are different ways of having sets. So some things are ordered, some things maybe don't necessarily have an order. You look them up by a key. So how many of you have learned about like a little bit of the theory of the speed of operations on some of those data storage types? Like what's this like there's like, have you heard of the big O notation, like O of natural log of n and things like that, depending on what type of data storage you have, or like O of 1, things like that. So every data storage type has its advantages and disadvantages. Some operations are super, super fast. Like if you look up something by its index in an array, it's super fast. But if you try to find the minimum element and it's stored as an array, you have to loop through the whole array to make sure that you find the minimum. So there's something called like the axiomatic set theory. We're not going to do that though. That's where you build up set theory from a series of axioms to make sure that there's like no contradictions, except of course the axioms themselves can't be proven, because you can, in order to prove anything, you have to appeal to like a higher level of math. That's called like Gödel's theorem. So you can't really ever prove something from nothing. So you always have to have something that's like left unproven, which are called the axioms. Another way of doing set theory is called naive set theory, which I think the book spells this wrong. Or at least it's maybe missing an accent mark. But let me just look where it says this word. Naive. It's talking about Georg Cantor. Did anybody remember that little story in the book about yeah, right here. Okay, so page 124, there's another option called naive set theory. And I think they're missing an accent mark or something from that word. So who knows what the word naive means? Like if somebody is naive, what does that stand for? like they're not experienced, right? Or like they're kind of like missing out on some basic facts of life. So this set theory has some logical issues. In fact, if you use that set theory too much, you can actually run into some contradictions. So that's what they call it, the naive set theory. So basically, it's just built on the idea that a set contains objects. Okay, now somebody's trying to call me. So that means I have to disconnect from the these meetings. Okay, so a set just contains objects, but the thing is, as you notice, there is no definition for object, right? So, for example, could you have a set that contains all sets? Well, that would be a little bit of a contradiction because then it would have to contain itself, and if it contained itself as an element, then it would have to contain another one of itself. So you sort of like keep going on forever. It wouldn't exactly make sense. So there has to be something bigger than even the idea of a set. But a set contains objects, or they call them elements. Elements. So what we're learning right now is kind of like learning some of the syntax of math. And by the way, let me just, you're Logan, right? Perfect. All right. Let's learn some of the syntax of sets. So first of all, let's learn about the size of a set. The size of a set is indicated by taking the absolute value of it is the number of elements of A, of the set A. Let me just say of the set A, so you know that it's a set. So another word for the size of a set is called the cardinality of it. The absolute value of A is also called the cardinality of A. The cardinality of A. So if A is equal to 1, 2, 3, so this, and this is like the roster notation that we learned, I believe, before, right? Did we learn any of the roster notation, or was that a different class that I was teaching? It's hard to remember which thing I said in which class. But we learned about the roster notation of a set, I think, and we learned about the set builder notations of sets, right? Did we learn about that? Like I said, you could also define a set by just saying like it's a set of letters X, such that like X is greater than 3, for example. Pretty sure that was in this class. So, so how many things are in that set? How many pieces of stuff are in that set? 3. 3. So the cardinality of it is equal to 3. So that's the one notation for sets. Now, if there's a total number of elements of the set, if the cardinality of A is equal to n for some integer called n, then A is called finite. So if you have a finite set, that means that there's a finite number of things in it. So all sets that are stored on computers obviously are finite sets because computers don't have an infinite amount of storage. But in math, you can have the idea of something that's infinite. So the definition of infinite is a little bit goofy in math. It just says if A is not finite, then it is infinite. Which is a little bit weird. So some sets have an infinite number of things in them. So that's all that that's saying. So what's an example of an infinite set? The set of positive integers, for example, is an infinite set. So how many positive integers are there? Well, every time you have one integer, if you add one to that, you'll get another positive integer, right? So you'll get it'll go on forever. So the set of positive integers is infinite because you don't have like a last or biggest one. What about the equality of sets? So how do you define an equal sign when you're talking about sets? So like the equality of numbers obviously is like 4 equals 4, right? How do you define what it means to say A equals B? So the equality of sets A equals B is true if and only if the elements of A are exactly the same elements. So not the same order necessarily, but the same elements as the elements of B. So for example, if I said 1, 2, 3, and I said 2, 1, 3, those sets are equal to each other because they both have the elements 1, 2, and 3, even if they're in a different order. So actually, with this actually implies that the set structure in math does not actually remember the order of elements in it. It's just it's a membership only type of relationship. So 1 is in this, 2 is in this, 3 is in this, 1 is in this, 2 is in this, and 3 is in this. Sets themselves don't actually possess an index or ordered number that tells which order each element is within it. So in fact, visually we can see that this is in 2, 1, 3 and 1, 2, 3, but mathematically the set itself does not contain information about what order they're in. If in mathematics, if you want to remember information about which order something is in, you have to actually put it in what's called an ordered pair or an ordered triple. It's kind of like a set, but it's written like this, 1, 2, 3, or like 2, 1, 3. If you put it with parentheses around it as an ordered pair or as an ordered triple, those two things are not actually sets and they do not equal each other. This represents X, Y, and Z. A coordinate in 3 dimensions that you're 1, 2, and 3, which is not equal to the coordinate in 3 dimensions of 2, 1, 3, and I'm missing a comma. So just remember, if you're talking about an ordered pair or an ordered triple or in anything that's in an n-dimensional space of points, those two things are not equal to each other. But with sets, there is no, this is not X, this is not Y, this is not Z. They're all equal as elements of that set. They're all just equally elements. There's no distinguishing between one or the other. So who remembers in mathematics in your college algebra about something called permutations and combinations? Remember that? Permutations, the order mattered, right? What about combinations? In combinations, the order did not matter, right? So when talking about ordered pairs or ordered triples, the order does matter, so those are not equal to. When you're talking about sets, it's just only whether it's a member of it or not that matters. So those things are equal with sets. Now let's talk about some common sets of numbers. So common sets of numbers. Okay, now there is one distinguishing thing between computer science. A lot of numbering systems start with 0 because mathematically you have to measure from where something starts to where it finishes. So if you're at the beginning of a day of like a certain section of memory in your computer, that's at the beginning of it, that's like 0.0. The end of the first object is actually a 0.1, which is the beginning of the second one. So a lot of numbering things in math start from 0. So they've done actually what's really a very terrible and sad mistake. But the first set of numbers in this book only, or maybe in discrete math only, it's called natural numbers. And the way to write the natural number set is to just draw a capital letter N. In fact, I didn't even quite do it right. Just draw a capital letter N like this, and then just draw one extra line beside it, like that. So the first way I did it was actually, I overlapped it too much. So the capital letter N with an extra line beside it, that's basically supposed to make it look like 3-dimensional N. That's called natural numbers. And in every math class, every real math class, well, I guess this is kind of a real math class, but in every math class that's not in computer science, natural numbers do not include zero because like you can't divide by zero. There's a lot of other issues with zero. And it's neither positive necessarily nor negative, and it's probably positive and negative. Like there's a whole lot of complications about zero. So they call them, the natural numbers are actually called counting numbers. If you see a deer, like this morning I actually saw 3 deer when I was running on the path. And they're all, I think, fawns, or like maybe a few months old fawns. You wouldn't count something if you didn't see it, right? So they call them counting numbers sometimes. So it starts with 1. So in actual math and in every other course that you'd ever have, and this is like the actual true definition of it, it starts with 1, 2, 3, 4, and it's anything that you could count, one or more of, is called a natural number or a counting number. But in this book only, and this is only because it's easier for them to use this for like things like arrays and stuff like that. And they really don't have a good excuse. In fact, they even put a comment in there. They said, we consider zero quite natural. So therefore they're putting zero. But of course you can't just put your opinion in math though. So this is the real definition of natural numbers. If you look up like any other kind of definition in a regular math textbook, that's what it actually is. But in computer science, and actually really in this book only because I've also taught discrete math from other textbooks, and this is not what they said. But in this book, this actually is one of the most popular books, if not the most popular discrete math book, though. But it's not a bad book. But according to this book, in this book only, and maybe possibly a few other ones, in this book, though, natural numbers is equal to 0, 1, which really messes up everything because, like, if you have a definition that says you can divide by any natural number, that would work fine in other classes. But in this book, you couldn't divide by any natural number because it includes 0. So this is the real definition, is 1, 2, 3, 4, etc. In this book, though, natural numbers. In fact, since that's not the real definition, I'm going to put like a little star by it, just to help remind you. So in this book, the natural numbers is defined as 0, 1, 2, 3, 4, etc. And it goes on forever. Then there's a number called z. Now you can't really draw a line by z like that because it makes it look like 1z. So they draw a line beside the middle part of it like this to make it look three-dimensional. So the set called z is a set of integers. Well, the set of integers would be like, it would include 0, of course. It'd be like 0, +1, -1, +2, -2. It would include all negatives and positives, like that. Now the set z plus, this is actually the set, this is normally the same as natural numbers. It contains all strictly positive integers. So which would be 1, 2, 3, 4, etc. So z plus normally would be the same as natural numbers. Then the set q, and you kind of draw like a line through the part of the q a little bit. Well, actually, that's too big of a line. You just draw it through the middle part. Like that. The set q is equal to, now you have to use set builder notation from this because it's complicated. It's a set of all integers divided by any other integer such that the top number is any integer at all, and the bottom number is any integer at all, except for one integer that you cannot divide by. Who knows what integer you cannot divide by? 0, right? Yep, and normally, you can actually define this in a different way. Normally, you don't have to say that q does not equal 0. You can say p is in any integer, which could be positive or negative. Then you could just say q is any natural number. But since they in their definition of natural numbers, they include 0, you can't actually just use the easier definition for rational numbers. So give me an example of a rational number that's not an integer. Can anybody think of a rational number that's not an integer? So give a rational number. So that'd be a number that's in Q. That's not an integer. Can somebody think of a rational number that's not an integer? Because integers are actually rational numbers themselves. But what is one rational number that's not an integer itself? And let me just check you in real quick. Yeah, let's see. Anthony, you're Anthony, right? Okay, perfect. All right. 133. Except, could you give it in the form of the like a fraction though? Yeah. So 1/3 would be an example of a rational number. So that's why they call it rational, is because anything that's like a fraction, a ratio. The word rational doesn't sound like a ratio, but it just means having to do with, like, made out of a ratio, basically. Rational. So rational number means like a ratio style number. That's what it means. A rational just means like a ratio style number. So like a ratio, which is a fraction. A ratio just means a fraction. So 1/3 is an example of a rational number that's not an integer. And then finally, the last but not the least, well, it's actually not even the last. The set R with a extra line beside it, that's called real numbers. That just means any number that's positive or negative or zero. It could be a fraction or an irrational number or a rational number or any number at all. Except, well, I shouldn't say any number. But it's any positive, negative, or zero number. Then the set of all positive real numbers, it's called all plus. That's called positive real numbers. Positive real numbers. And finally, we're not going to probably get into this very much in this class, but the set C, with sort of like an extra line through the C, this is called the set of all complex numbers. Who remembers complex numbers from college algebra? So a complex number could be something like 2 plus 3i, or it could also just be 2 as well. So complex, because 2 is in the form of 2 plus 0i, etc. So complex numbers could include the real number as well as the imaginary component. And like we learned about in college algebra, complex numbers are definitely actually real in the real world. They represent things like alternating current, which has phase shift and amplitude both. It carries energy in two different ways through the electrical wire. So um, so there's some basic sets for you. And let's try to diagram some sets real quick. So let's write a set of big numbers. So first, all sets are analyzed in a context of some implied, or maybe sometimes it's clear, some implied universal set. Hold on, let me spell it the right way. Universal set. So all sets are analyzed in the context of some implied universal set called U for short. Boom. Okay, so a Venn diagram basically is a box that represents that universal set. So draw a box and then label that box U. Boom, like that. And then whatever other sets that you have are put inside of that box, usually in the shape of circles. So let's just say that U has all positive integers from 1 through 10. So let's say we're restricting our universe to 1, 2, 3, all the way through 10. Now let's put this set of even numbers from 1 through 10, which would be 2, 4, all the way through 10. Odd numbers, that looks like 0, but I'll just say odd for short. 1, 3 through 9. And then prime numbers. Who knows what the prime numbers are from 1 through 10? 4, 6, 3, 2, 3, 5, 7. 2, 3, 5, 7. Yep. Because why is that? Because no number goes into 7, for example, other than 1 and 7, right? 2 doesn't go into 3, 4 doesn't, 4 doesn't, etc. So any number that doesn't have any factors that go into it except for 1 in itself is called a prime number. And those are very special numbers in a lot of different things. In fact, that's how prime numbers or how RSA cryptography works. Okay, so there's prime numbers. Let's draw those sets in here. So let's put the even numbers, maybe. Draw a circle for the even numbers first. So 2, 4, 6, 8, 10. Now let's draw a circle for the odd numbers. So 1, 3, 5, 7, 9. Are those sets overlapping? Whoops, sorry, accidentally touched. No. They're not overlapping. That means if they're not overlapping, they're called disjoint. So disjoint sets have no common elements. So that's the opposite of being equal is being disjoint, basically. Well, actually, no, I shouldn't say that because some sets, if you have a set that has nothing in it, then technically it's disjoint, but it still has all the common elements. Okay, so there's that. So the odd numbers are disjoint from the even numbers. Okay, what about the prime numbers though? Where would that circle go? So let's go to like blue. The prime numbers would be 2, 3, 5, 7, right? Would actually overlap both circles. So the prime numbers actually overlaps both parts. And probably does not overlap both parts. So there are that's the diagram of those. The blue numbers, I'll circle the prime numbers in blue. And the even numbers, you can see those are the evens and those are the odds. Now let's talk about some set operations. Wait, did I already talk about set operations? Like union? Okay, so I think I actually already did. So let's go ahead then. We already talked about set operations. Let's maybe review that just a little bit. Just a little tiny bit. And there's also one set operation that we didn't talk about. Okay, so what is the result of this? Even numbers intersect prime numbers. What is the intersection of even numbers and prime numbers? What's the intersection of even numbers and prime numbers? What's the intersection of even numbers and prime numbers? What common numbers? 2, 5. Well, just even numbers. This is just good. Yeah, the only intersection that's in common between even numbers, those numbers, and prime numbers, which is the blue numbers, is the number 2. Right? What's the intersection between odd numbers and prime numbers? Yep. So in human language, we would say, what odd numbers are prime numbers? That basically means odd intersect prime. And then the first one, even intersect prime, is like saying, what even numbers are prime numbers? What's the intersection of odd numbers and even numbers? So there's none. How do you say a set that has none? Two ways. You can just say it's a set with nothing in it, like that. Or there's a symbol for that. It's called phi. It's like a zero at the line through it, going diagonally. Now the line has to be at a 45-degree angle to kind of come out both ends. Otherwise, if you just draw like a circle like this, that's just zero. That's just a different way of writing zero. But if it comes out of both ends and it's a 45-degree angle, then it represents the empty set. This is called the empty set. Perfect. All right. Are the prime numbers a subset? Let me ask you another question. Are the prime numbers a subset of even numbers? So are the prime numbers, you'd write it like this, within the even numbers? Are all of them within the evens? No, right. So prime numbers are not all within the even numbers. Are the prime numbers a subset of the odd numbers? No, because there's one, it's close, but there is one prime number that's not an odd number. In fact, actually, you might think, well, that's kind of sad because they're almost all odd. But actually, once you get to any other number, there's never any more of that either. So like once you get past 2, no other prime numbers are divisible by 2. Once you get past 3, no other prime numbers are divisible by 3. Once you get past 5, no other prime numbers are divisible by 5. So actually, even numbers, there's really nothing special about even numbers. Even numbers are just numbers that are divisible by 2, right? And if we could have another word like even numbers or something, which could represent all numbers divisible by 3. Then we could like say even numbers that are like all numbers divisible by 5. So there are no other even numbers in the prime numbers after 2, but there's also no other numbers divisible by 3 after 3 and so forth. So prime numbers are kind of mysterious. Do you think there's ever a point in which you get beyond all numbers that you don't have to have any more numbers that are not? Or do you think you'll ever get to the end and there's just no more prime numbers at all? Don't think so. Okay, good idea. Okay. Let's talk about something called the Cartesian product then. Have I mentioned that yet? Cartesian product. So what if I said A times B? Except in this case, we're overloading the multiplication operator. Who's ever heard of overloaded operators in computer programming? Do you know what that means? If you take an operator and apply it to something that it's not really the data type that it applies to, sometimes it can actually be defined to perform an operation anyway, but in some other way than it normally does. Have you ever heard of that? So where basically this operator is now being overloaded, like applied to an abnormal situation, applied to an unusual situation, I'll say. So it's not a number multiplied by a number, it's a set multiplied by a set. So A cross B is just defined as an ordered pair. I'll just say X and Y. Says that X could be any element of A and Y could be any element of B. So what's the Cartesian product of prime numbers 2, 3, 5, and 7 cross product with the numbers, let's just say X, Y, and Z. What's the cross product of 2, 3, 5, 7 with X, Y, and Z? It would be a set that contained pairs of numbers so that the first number in every pair was always a prime number, either 2, 3, 5, or 7. And the second number from every pair was either X, Y, or Z. So it could be 2X. Sorry, hold on. It's not Y and Z both. It could be 2 with an X, 2 with the Y, 2 with the Z. Have you ever wanted to try every possible combination of toppings on your Wendy's hamburger? There's supposedly like 500 different combinations you could have. This is kind of what that's like. So 2 with an X, 2 with the Y, 2 with the Z, or 3 with an X, 3 with the Y, 3 with the Z, or it could be 5 with an X, 5 with the Y, 5 with the Z. What else could it be? What's the last one? What's the last 3 ones? I mean, what's the last one that could be part of the cross product? 7 with an X, 7 with a Y, 7 with a Z. I've got a question. What's the cardinality of the cross product? What's the cardinality of A cross? Sorry. What's the number of elements of A cross B?
Oh,
Yep. And what does 12 happen to be?
number of items in A times.
Yep. Number of items in A times the number of items in B. So that's just kind of like a deductible observation. Because for every number that's in one, you can pair it up with the number in the other one. So the cardinality of A cross B is the cardinality of A times the cardinality of B. So it can get very big very quick. Another related rule to that is the cardinality of a cross product is also the cardinality of the power set. There's a set called the power set. The power set. Now in math, it's a very weird notation in math for the power set. In this book, they just use a strange looking like cursive letter P like that. I actually did pretty good, but it's kind of hard to write. It's not exactly the way the book does, but the P of a set A is equal to the set containing all possible subsets of A. So I'm going to give you an example. If A has 2 things in it, 1 and 2, what's the power set of A? So there's actually going to be 4 things in the answer. So by the way, it's a set of sets because it contains all the subsets of the set. So it's a set of different subsets. So first of all, a set itself is always a set. Whoops, I'm always writing too fast. A set itself is always a subset of itself. So the power set always contains the original set. But also the number of the set that contains just 1 is part of the set that contains 1 and 2, right? The set that contains just 2 is also part of the set that contains 1 and 2. And then the final and last set is a set that contains nothing. The set that contains nothing is always a subset of every set. So the power set of 8 is like saying, what choices could you have? Let's say if you're trying to be nice to somebody and they're visiting your house and you cook like some food for them. And you have like blueberries and strawberries, let's say. The power set is all combinations of food that they could take from your house. If you had blueberries and strawberries, they could take their set of choices could be blueberries and strawberries, or it could be just blueberries, or it could be just strawberries, or it could be that they don't want anything because they're just like on a diet or they're like just mean. So that's the power set. The power set basically means all possible choices from out of a set, including all the choices, or some of the choices, or none of the choices. What's the cardinality of a power set? By the way, let me actually explain to you one cool thing. This will help remind you of this. In math, the power set is often called 2 to the power of the set. This is the notation used in much of math class, in like a lot of other math classes. So this is the notation in math. Now it looks really weird. That looks even weirder than saying P of A. 2 to the power of A. How do you even take 2 to the power of a set? That's impossible in math. You can't actually raise 2 times 2 times 2 like to the number of a set, because a set isn't a number, right? But that's another example of overloading an operator. They're overloading the exponentiation operator to extend it to the case in which the power isn't a number, but it's a set. So that's just another example of that. So when you have a set on the power of 2, in math, people will automatically know that that means the power set. So what is the cardinality of the power set of A? Let you think about this for a while.
Side A squared.
Close, but not quite big enough though. And J in general is not quite big enough. So remember this. If you have an empty set, the power set only has one thing. So if you have 0, you get one thing in the power set. You get an empty set, which is what, one thing. If you have one thing in your power set, if you have one thing in the original set, you could get two things in your power set. You could either choose that one thing, or you could choose nothing. So you could either choose it or not. You'd have two options in your power set. Now, what if you have two things in your original set? Every time you add one thing to your original set, it doubles the number of items in your power set. Because everything that you had in your previous power set, if there's one more option to choose from, you could choose any of the previous options, either with or without the next option in your set. So every time you add one element to your original set, it adds twice as many options in the power set. Because every option you had, but like, for example, if I added to the blueberries and strawberries, if I added grapes, then every single one of these choices of blueberries or strawberries, you could also add, you could either choose grapes with each of these options. You'd have 4 options with grapes, or you could have 4 options without grapes, right? So you'd have 8 options. So it's always twice as many. So what is it called if you have a certain number of options and then you have twice as many? Then you have twice as many, and then you have twice as many, and then you have twice as many. What was that called? That's called 2 to the power of, like, it's an exponential amount of 2, right? So it's 2 to the power of the cardinality of A. That's the cardinality of the power set. Okay, perfect. The very last thing in this section is just called something called a truth set. The truth set is not exactly a specific notation for it. The truth set is just the set of a proposition. So if you have a proposition P, it's just the set of all x values within a set such that the proposition is true for that element of the set. So of course, if there's a true set of P, there's also a falsehood set of P, which would be all the sets within this set such that it's not true, but the proposition is true. So that's called the truth set of a proposition. So that is all there is for today. But remember though, make sure you come back on Friday because we're going to have a special ceremony of excellence on Friday. But I would also recommend that you look at page 136. Go to page 136 and study all the set identities. All right. Well, good luck, everybody. Let me just look at the attendance real quick and make sure I didn't miss anybody. Okay, so Noah, is Noah here? Okay. Yeah. Yep. Thank you very much, everybody.
Thank you.
You're welcome.